star decay is actually the inhomogeneities caused, there's not a perfect field out there, okay? So how I like to describe the inhomogeneities are like what?
They're not even.
What did you call them? They're the ones that kind of stray off the beaten path. And why do we not want them or like them? Typically.
They don't help the image.
Correct. Correct. They're not contributing positively to the image. They're creating havoc, we'll say. Okay? So while this is happening, while this dephasing is happening in T1 and T2 and T2 star is occurring, in order to clean up the T2 star decay, how do we do that? A rephasing pulse. It's a 180. Why would we want a 180?
We want to get it out of the transverse plane.
We want to sweep it past the transverse plane. Get it the hell out of there, right? Get it gone. So 90-degree excitation pulse followed by a 180-degree rephasing RF pulse is called a what?
Spin echo.
Spin echo. Yay, I did get it. That's good. Yay. Okay, so the 90-degree RF pulse, the first one that's delivered is an excitation. The 90 sends them into the transverse plane. The 180, now remember, the 90 comes down, the 90 gets turned off. Dephasing begins. Before dephasing, which is during the dephasing phase, is when T1, T2, and T2 star occurs, okay? The 180 rephasing is sent in to get rid of that T2, to get rid of the inhomogeneities or the T2 star decay, okay? Does that make sense? So once that 180 has passed and it's swept that T2 star decay past the transverse plane, T1 and T2 continue, okay? Make sense? So that is called a spin echo. 90-degree excitation pulse followed by a 180 rephasing pulse. There's another type of pulse sequence that we're going to talk about tonight, and it's called a gradient echo. Did we start on that last week at all? We completely stopped. All right, our brains were fried. Okay, so let me review a little bit more. In spin echo, we can produce what kind of images? Let's talk image weighting. What are the three different types of image weighting that we've talked about so far? T1, T2, and proton density. And we know in order to produce either one of those three, how do we control that? How do we control what type of image contrast we produce? By the TR and the TE, right? Okay, very good. So TR, definition of TR is what?
Repetition time.
Repetition time, and what does that mean to me?
The time between each excitation.
Excitation pulse to the next excitation pulse. Because remember, there's not just one excitation pulse sent in and boom, we get an image, right? It's multiple. It just keeps happening. 90, 180, 90, 180, 90, 180, okay? So we've learned two parameters, TR and TE. TR defined as the time between excitation pulses, correct? What does TR control?
T1.
T1 weighting. So if TR controls T1 weighting, where do we want to keep our TR? In a T1 weighted image? Short. What does that TR, we say that it controls T1, correct? How does it control T1?
Allows for recovery time. Allows for recovery time. So either you shorten it so it doesn't give it enough time to recover for the
Correct. MRI is based on what?
Fat and water.
The T1 and T2 times the fat and water. So depending on how we set our TR and our TE is going to depend on whether fat is bright or dark or water is bright or dark, correct? So T1 weighting, we're going to use a short TR to maximize T1 weighting, correct? What does TE control? T2. So what will our T2 be like for a T1?
Short.
Did I say T2? I meant to say TE. What will our TE be for a T1? For a T1. Short. Why?
You don't give it enough time to decay.
To prevent the full decay, correct? So the TE controls T2. So for a T1 weighted image, we want to maximize T1 by using a short TR, and we want to eliminate T2 by using a short TE. Okay, so using that same principle on a T2 weighted image, our TR should be what? Why? Eliminates T1. And what should our TE be? Long to accentuate T2. So we have T1 over here, T2 over here. What do we have in the middle? Proton density. What is a proton density weighted image? It's not a T1 and it's not a T2, right? So in order to eliminate T1, what do we need to do with our TR? Make it long. In order to eliminate T2, what do we do with our TE? Short. Okay, so T1, short TR, short TE. T2, long TR, long TE. Proton density, long TR, short TE. Make sense? Okay, so we've got image weighting. We got a handle on that, right? We've got a handle on spin echo, correct? All right, let's talk about gradient echo now. This is another way to excite and rephase the spins, okay? So, spin echo uses the 90-degree flip angle, okay, or 90-degree RF excitation pulse. Now we can start to refer to it as a flip angle because it's flipping the protons into the transverse plane. When you look on those GE brats in here like myself, if you look at your parameters, it'll say flip angle. Okay, that is your 90-degree excitation pulse. Okay, or your, let's say your excitation. How many degrees it is. As soon as you see 90, we automatically know it's what? Spin echo. A spin echo. 90-degree excitation pulse followed by a 180 rephasing. Okay? A gradient echo is going to use a variable flip angle, typically less than 90. Okay? So spin echo uses the 180 rephasing. Gradient echo is going to use a gradient. When we talk gradient echo, everything's gradient. Okay? We don't use an RF excitation pulse in a gradient echo to excite the protons or to flip them over. We use a gradient, okay, with a variable amplitude. We're going to use a gradient to flip those spins. Okay, so the difference between spin echo and gradient echo is spin echo uses a 90-degree excitation pulse to flip the spins. A gradient echo uses gradients with a variable flip angle, typically less than 90, to flip the spins into the transverse plane. When we turn off either one of those excitation pulses or excitation methods, dephasing always occurs. In a spin echo, we use the 180 rephasing pulse to rephase the spins, okay? In gradient echo, again, we use gradients to do the rephasing. Okay, we're going to get a little bit deeper into that, but those are the two main differences between spin echo and gradient echo. Everybody with me? Spin echo, 90, 180. Gradient echo, gradient, gradient. Okay? All right, so Gradient echo uses excitation pulse with a flip angle less than 90 degrees, okay? Only a portion of the NMB gets flipped over into the transverse plane. So right then and there, what does that already tell you? If only a portion of the NMB is getting flipped over into the transverse plane, unlike a spin echo, the entire longitude, the entire NMB goes over into the transverse plane. Our signal is going to be less because not all of the NMB is going to get over into the transverse plane. Okay? I think somebody over here said that. Sure you said okay.
Yeah,
So rephasing is done by using gradients, not an RF 180. What does the 180 do? It sweeps them right past. So it gets that T2 star, boom, out of the imaging area. Okay, so we're not using any of that for imaging. When we talk gradients, a gradient echo, the gradients just go right on top. They do not go at a 180. They do not sweep that T2 star past the transverse plane. So that T2 star contributes to the image. So our signal goes down. Okay, they're not as pretty of an image because now we've got the serial killers and the stragglers contributing to the image. Okay, so what happens with a gradient echo, when that gradient gets turned off, the excitation gradient gets turned off, and the spins start to dephase, to get them to rephase, a gradient of opposite polarity is put down on top of the spins. What does that mean to us? Okay, remember when I told you guys that some of the spins at one end will be faster, some at the other end will be slower? Okay, so how does a gradient echo get rephased? A gradient echo gets rephased by putting a gradient of opposite polarity right on top. So let's say these spins over here are going very fast, and these spins over here slow down. The gradient that's applied, this part of the gradient will be the slow part that will slow those spins down, and this part of the gradient will be the fast part, which will help those slow ones to speed up so that they all get back together again. Does that make sense? So to rephase the spins in a gradient echo, a gradient of opposite polarity is put down on top of those spins. Okay? And this signal that we get from this using the gradient is known as a gradient echo. So a spin echo, 90-degree excitation pulse, followed by a 180 rephasing pulse. Gradient echo uses a gradient to flip the spin, a variable angle, usually less than 90, to flip the spins over. Not all of the NMB gets over, only a portion of it. So automatically, we have decreased signal, okay? When we put that gradient on to rephase the spins, it cannot compensate for T2 star decay, okay? How do we get rid of T2 star decay? With that 180 that flips, that sweeps that T2 star decay all the way past the transverse plane so it does not contribute. With a gradient echo, we cannot compensate for T2 star decay, okay? Because that gradient that's used to rephase only touches right here. Anything that's out here, any of the inhomogeneities that are out here are contributing to the image. Make sense? All right. So dive a little bit deeper. So gradients. By applying the gradients creates a secondary external magnetic field that will interact with the spins. That's that gradient that I'm telling you guys about, okay, of opposite polarity. Okay, so if this is the fast end and this is the slow end, this will be the slow end and this will be the fast end to get them to all group back together. So magnetic field along the axis of the gradient, it gets altered in a linear fashion. Isocenter always remains unchanged, okay? Isocenter is always going to have the same exact strength at all times. As you get away from isocenter, you have it's in a linear fashion. So you guys know what linear means?
Yeah.
Yeah, stronger at one end, weaker at the other, okay? So again, as the gradient flips the spins over, some of them will see, once it gets turned off, some will speed up, some will slow down, just like in a spin echo. That gradient gets put on top of them in opposite polarity. So fast end, slow end, fast end. Make sense? That's how we rephase the spins in a gradient echo pulse sequence. All right. So polarity. On one side of isocenter, the magnetic field gets stronger, and on the other side it gets weaker. The direction of the current in the gradient determines which side will be stronger and which side will be weaker. So the direction in the current of the gradient coil becomes the polarity. Again, if this is the fast end and this is the slow end, they speed up here and they slow down here. When that gradient of opposite polarity comes down, fast end to the slow end to the fast end, okay? To get them all to regroup again. Make sense? So what is the effect on precession? Obviously, it spins in a stronger field. They're going to speed up, right? Precessional frequency will increase. Spins in the weaker side of the field will slow down. Precessional frequency will decrease. Okay? Okay, so when does dephasing occur? As soon as the excitation pulse gets turned off or is removed. Some spins will speed up, some spins will slow down. By using gradient rephasing, again, I know I'm hitting this, probably beating this horse, right? We apply that gradient of opposite polarity so that the spins in the spins are in a stronger field, the slower spins, and they will start to speed up. The same gradient will be weaker at the location of the faster spins and cause them to slow down so that they all come back into harmony together. Okay, so one end's not faster and the other end's slower. This forces the spins to rephase. The signal measured is called the gradient echo. So spin echo is 90-degree excitation pulse followed by 180 rephasing pulse. What does a 180 rephasing pulse do? It rephases the spins, but it also cleans up the T2 star decay, the crap, the serial killers, the stragglers, whatever we want to call them. Okay? When we do a gradient echo pulse sequence, how do we excite or how do we flip the spins over into the transverse plane? We use a gradient
Less than 90.
with a flip angle of less than 90 degrees. What does that mean by using a flip angle less than 90 degrees?
Not all of them get down to the transverse plane.
Correct. Not all of the NMB will make it over into the transverse plane, which means what?
To another, to sit up top with the opposite polar.
Hang on.
Am I going too
Before
far
that,
ahead?
you're going too fast.
Okay.
You're a step ahead. What does that mean if all of the NMB does not get over into the transverse plane?
Low signal.
Or signal, we lose signal, okay? So if we really think about it, if we're not sending all of the NMB over into the transverse plane, how does that affect our parameters that we use? Mike, do you know? How would that affect our parameters?
It would be shorter.
They'd be shorter. If we're using shorter parameters, what else would be affected? A little bit. What about our time? Be quicker, right? So, Spin echo pulse sequences are longer because the entire NMB is being pushed over into the transverse plane, okay? When we use gradient echo, the entire NMB does not get flipped over, so now we can use shorter times. We can use shorter TR and TE, which will also affect our time and our signal. Okay, so that's advantages of gradient echo. Obviously, is a timing factor, right? It's much faster than using an RF rephasing pulse. This will allow for significant reduction in our TE. TR can also be reduced because only part of the NMB actually reaches the transverse plane. Thus, T1 recovery, think about it, will occur a lot quicker, right? Because not all of the NMB gets flipped over. So this will ultimately reduce our scan time. So gradient echo pulse sequences, an advantage to them is definitely a time factor. A disadvantage is
Low signal.
our signal. Okay, our signal will go down. Disadvantage, another disadvantage of gradient echo is that gradient cannot compensate for the T2 star decay, the inhomogeneities in the magnetic field. So in gradient echo, T2 weighting is always referred to as T2 star weighting because it's very heavily weighted by that T2 star decay. That signal gets picked up, it gets used. Okay, so it's not a true T2 weighted image. It's now called a T2 star weighted. So T2, or gradient echo is extremely susceptible to magnetic field inhomogeneities. Why? It does. You can't compensate for it. The gradient cannot compensate for the T2 star decay. What else is T2 star decay known to us? The inhomogeneities, right? It's those stragglers, it's the negativity that we don't want in our image, okay? So gradient echo is very susceptible, very susceptible to magnetic inhomogeneities. So there's a high amount of magnetic susceptibility artifact from any type of ferrous material. How many of you have seen patients that have had a knee replacement or fusion in their neck or their back? Okay? That signal void is actually magnetic susceptibility. Okay? So when we're scanning patients that have any kind of metal, the last pulse sequence that we want to use is what? A gradient echo. Why? It's very susceptible. We can't clean up the magnetic susceptibility or the inhomogeneity. Remember that gradient cannot compensate for magnetic susceptibility or the inhomogeneity. So what pulse sequence should we be using?
Spin echo.
Spin echo. Why? Because it can compensate by using that 180 rephasing pulse. Does that make sense? Okay, so spin echo, 90-degree excitation pulse followed by a 180 rephasing. What's a fast spin echo? Anybody? Multiple 180s.
2 or more.
2 or more. Okay? The more 180s you send in, the more fat that's going to get cleaned up. Okay? So anybody that has metal, the pulse sequence not to do is gradient echo. Why? That gradient cannot compensate for the magnetic susceptibility or the inhomogeneities. Okay? We want to use a spin echo. Why? What will clean up? What will clean up the inhomogeneity?
The 180.
The 180s. Okay, so spin echo, yes, is good for patients with metal. What's even better for patients that have any kind of metal in them? Fast spin echo, because the more 180s you use, the more it cleans it up. It's not going to get rid of it. Okay, you're still going to have a signal void in that area, that the metal, you know, whatever is there, but it will help to clean it up.
Is that what you call grappa? Or is that something totally different?
That's Siemens talk.
Yeah.
Talk GE, talk to me. Just kidding. We use pulse sequences, those and any of my GE people there. We use pulse sequences called FSPGR, which is a fast spoiled gradient recalled echo. Every manufacturer has a different name for it, so I'm sure grappa is probably your gradient echo sequence. Yeah. Yeah, ask them tomorrow. I'm pretty, like I said, I don't really speak GE, so I can't speak for that, but I'm pretty sure that's probably what it is. Okay, but once, like, basic pulse sequences, how it all started in the beginning of time when MR was first invented or discovered, it was 2 pulse sequences. Spin echo, gradient echo. And now we've come leaps and bounds from there. But the basis to start bottom, right on ground level before we build up, spin echo, gradient echo. Spin echo is 90-degree excitation pulse followed by a 180 rephasing pulse. Gradient echo uses a gradient at a variable flip angle, typically less than 90, to flip the spins, uses a gradient to rephase the spins. Okay, so we have spins in longitudinal, in equilibrium. We send in spin echo. We send in a 90-degree excitation pulse delivered at Larmor frequency of hydrogen, depending on what field strength we're at. That excitation pulse flips the spins over into the transverse plane. Once they're over in the transverse plane, now they are in phase. Okay? Next thing we do is we turn off the excitation pulse. The fins. Why do I keep wanting to say fins? The spins will begin to dephase. Just as they're beginning to dephase, we send in
180
a 180 rephasing pulse, okay, to clean up that magnetic susceptibility, the the field inhomogeneities, the T2 star decay, okay? Once that happens, T1 recovery, T2 decay begins. What happens next? Whether we're in a spin echo or a gradient echo, once we turn off that RF excitation pulse, the spins dephase, the 180 rephasing pulse is sent in, then that's turned off. T1 and T2 are occurring. What happens now?
Signal receiving the coil?
The signal gets received or picked up in the receiver coil. What happens next?
Sound is transformed into an image.
FID, I don't know.
The FIT. What is the FIT? It's a free induction decay, but what is it? Correct. As soon as that excitation pulse is turned off and that 180 sweeps past, the signal gets received in the coil. The signal begins to decrease because we've turned off, right, that excitation pulse. So now we're picking up that signal that is being sent off by the protons or the spins into the receiver coil. It becomes what we call a free induction decay or a FID, and it's the decrease in the signal, and it gets picked up in the receiver coil. Then it gets sent to the array processor. The array processor uses complex mathematical equations to give each signal I'll place on the grayscale to create an image. Now, if I want to create a T1 weighted image, that means I want fat to be
Right.
and fluid to be
Dark.
very good. If I want to create a T2 weighted image, that means I want fat to be dark and fluid to be
Right.
very good. When we look at a proton density weighted image, it's in between. We're not quite bright, we're not quite dark, we're kind of, I like to say mellow. Just kind of mellowed out, right? Because your fluid's still a little bit dark, right? Your fat's still a little, everything's kind of like grayed and dark and mellow, right in the middle, okay? So, disadvantage of gradient echo, gradients cannot compensate for that T2 star decay. So, T2 weighted images in gradient echo are now known as T2 star weighted, okay? You get a high amount of magnetic susceptibility artifact from any ferrous material. Like I said, if the patient had C-spine, they had a fusion, lumbar fusion, knee replacement, that will be what we call very high magnetic susceptibility. And gradients cannot clean that up. So the gradient echo is the worst pulse sequence to do with a patient that has any type of metal in them, okay? All right, so parameters, let's talk about parameters in gradient echo. We already know in spin echo, to get a T1 weighted image, Jamarli, what are my parameters for a T1 weighted image? What's my TR? Go ahead.
Short PR?
Yep, and a,
Long TV?
not, not,
Short T.
and a,
Short TV.
why a short TR?
Because then we won't give enough time for
What is TR control?
T2. No, TR controls T1.
TR controls T1. So in order to get a T1 weighted image, we want to accentuate T1, and how we do that with our TR by using a short TR. We want to do what with T2? We want to eliminate it. How do we eliminate T2? What parameter controls T2? TE. So to eliminate T2 in a T1 weighted image, how would we set our TE?
We need a long TV? No, we need a short TV.
Short TE.
Because then it won't give it enough time to...
To decay, correct. So T1 is always short TR, short TE. Now if I want to create a T2 weighted image, I want to eliminate T1. So how do I eliminate T1?
Short TV and a long TR, or I'm confused.
Okay, you are confusing yourself. TR controls
T1.
T1. To